Swayam Prabha. Digital India. Educated India.
Good morning everybody. We are trying to look at how an acoustic field and a flame couple together to make thermoacoustic instabilities. I will show some demonstration of how this happens. First we will see the video of a real experiment. So we can have this experiment in a very simple way. You can do it at home by taking like a candle or a Bunsen burner flame and put a glass tube around it, and you can repeat the same kind of thing that is here. So all we have here is there is a pre-mixer for, we are looking at pre-mixed flame. So we are mixing LPG and air here, bring it into a decoupler here, which is like a large volume to stop the fluctuations or whatever, make everything uniform, and then you send it out through this tube, and there is a burner here, you can burn here, and you can either have a single Bunsen burner type flame, or you can have more fancy things like multiple burners. So you can have multiple flames with flames at each of these holes standing, and then you put a tube around, and you can have the tube with you can have a tube which has a open end or a closed end. If there is an open end, there will be draft, or if there is a closed end, there will be no draft, but either way you can, so you can simulate a closed open end or open end, whichever you want, and you can make the pressure measurements with microphones, and you can use a high speed camera to do imaging or a regular camera to get a video, and we can get the chemiluminescence imaging with a photomultiplier tube with appropriate filter. So your flame has radicals, so if you put a filter corresponding to CH radical like 428 nanometer, you will image the blue which correspond to CH filter. If you put a 308 nanometer filter, you can image the OH in the flame. So these radicals are there present only in the reaction zone, whereas you will see the whole flame to be luminous because there is a black body radiation from the hot gases, and you will see everything. So in a regular movie what you see will be the flame luminosity, so that you would see a bigger region, but the reaction zone where these actual reactions happen, you must have studied in premixed flame. There is a preheat zone, then there is a very thin reaction zone, and then there is the products. So the reaction zone would have that is the region where you have this radical CH, CC, OH, so you can look at the chemiluminescence from any of these radicals. So these are the things that you can do. It is a very simple experiment, and you can set up whatever equivalence ratio you want. You can vary the equivalence ratio, try all kinds of things, and then you can track the evolution. So in a mathematical model you have to solve the differential equation to see the evolution, but in a reality you just have to look and you can see the evolution. It is an experiment. So we actually have a Bunsen type flames. It's there on the video. Thanks to Lipika Kaviraj who gave me this picture, and sorry, 1 second. Let me show you a video of this image, video of this experiment. So there is a flame you can see, and I will there is actually a duct, but I mean because it's dark everywhere except the flame, so you don't really see the duct, but there is actually a duct here, but it's not illuminated. We are just imaging just the luminosity from the flame, and you can see the video as well as hear the audio which is coming. Okay, so you heard that. So this is nice limit cycle oscillations that occur when you have the fluctuating heat release from the flame coupled with the acoustic field. Now the flame looks very steady in this picture. That is because the flame is oscillating at about 200 hertz or something, and our eyes cannot track the 200 hertz, nor can that particular camera track the 200 hertz. So what we do is we image with a high speed camera something which can do 2000 frames per second or a few thousand frames per second, and then play it slowly so that our eyes can see it, because even if you take it at 2000 frames per second and you play at 2000 frames per second, you would not see anything. So what you do in high speed movies is you take the video at a very high speed, 5000 frames per second or 6000 or 2000 frames per second at a rate much faster than the frequencies involved in the system, and then you play slowly. So you would have seen in cricket match they show the ball going turning and very nicely and then moving and all that, and diving in slow motion. So you acquire a large number of frames, so that's the meaning of high speed video. Normally you take 30 frames per second or 25 frames per second, you take much larger than that and play it slowly so that you can sense what happened in the short time, but you are kind of expanding the time. I hope this is clear. So if you now see this, so you can see that the flame is actually wrinkling, and so if you look at the wrinkles on the flame surface, and you can have, depending on the frequency and the amplitudes that are involved, the wrinkling can look differently, and you can have small amount of wrinkling, large amount of wrinkling, that's all dependent on the experiment. But as a result, the important thing to notice is the flame area is fluctuating. So if you have a steady flame, you have like a tent like flame or something like that, like a cone or tent, and then because the wrinkles are coming, so anytime a flame wrinkles, the area is changing, it's increasing compared to the steady shape. And when you increase the area or decrease the area, when you change the area, we are basically altering the amount of fuel that is consumed, because as long as there is a flame, everything that goes through in a premixed flame is consumed, because we are looking at leaner flames. I mean, if you are of course having rich flame, only the whatever is the balanced mixture ratio will be burned, there will be excess fuel, but if you are having a lean fuel, everything will be burned. So whatever is going through the flame is being consumed. So as long as you have a flame area, you are consuming everything that is coming. So if the flame area is wrinkling, that means you are having at some instant more area, some other instant less area, so that means you are consuming more at some instant, consuming less at some instant. So that is what is the heat release rate, and the acoustic field is setting up velocity fluctuations at the flame, which is perturbing the flame, and we have to look at that. I hope this is clear what I am explaining. You have seen this now, okay. So we can also do multiple flame experiments. So instead of a Bunsen burner flame, so in here if you put a burner of this shape, you can set up several flames, and we can see that. I mean, in reality in many combustors there will be this kind of configuration. This is like a standard configuration which many people study. Let me play the movie, the video. You saw that, I'll play one more time. So once again the flames are actually oscillating, we are unable to see it because I mean it's oscillating too fast, so we have to do the high speed imaging, and if we do that, so this is how the multiple flames look like. Yeah, unfortunately you can see 3 flames on the screen, but there is only one because it's too bright. So we can look at the high speed imaging. There is actually a flame here and a flame here. If you see carefully you can see it. So you can see they are oscillating. I'll play it again. So again the flame is oscillating back and forth, the flame surface area is increasing and decreasing. This is what is making the flame consume more mixture at another instant, less mixture at another instant, and therefore the heat release is more at some instant, less at another instant. So you have fluctuating heat release, and we are in a confined environment, so there is acoustic oscillations and we are having a feedback. Now which is the message of this slide? So the okay. So the oscillations make the flame wrinkle, wrinkling leads to oscillatory heat release, so Q prime correlates with area fluctuations, and so we need to solve for the area fluctuations of the flame. That is the crux of the matter. So given a heat release rate, we know how to deal with the acoustic field. That is what we did. We wrote the equations, we had a momentum equation and we have an energy equation, and an energy equation had a heat release term in it. So we know how to deal with it provided you put the heat release term in. In the earlier example we put a correlation for heat release given by Maria Heckel. Now instead we need to put the heat release rate fluctuation that you will get from the premixed flame. So how do you do that? So we need to see what happens to a flame when there is a velocity fluctuation. So it will have a lagged response and so on and so forth. So we have to solve for it, and once you solve for this you can input into the acoustic equations and then solve them in a couple manner, either in the time domain or we can do the whole analysis in the frequency domain like we did otherwise. So the objective now of the lesson is to write the appropriate equations, simplest possible equations for a premixed flame, and try to solve for the flame shape, and once you know the flame shape you can get the wrinkling and the flame area, and once you know the flame area we know that we can, from the flame area we can get the heat release rate. Is this clear what we are trying to do? Any questions about this?
Flame oscillation. There is naturally is possible.
So yes, what in the movies that I showed here, what we are doing is we have the, see you must have understood from the everything we did earlier that at some locations flame will be stable, some other locations flame will be unstable. So I can keep the burner at some location where the flame will be stable, light the flame and eventually it will stay stable, and then generally move it to a location where the flame where the instability can come in. Now to initiate, if you are in a I just use a traverse to move it. Yeah, I move the tube here. You can either move the flame or the tube. In this particular experiment I have a picture here, one second. So in this experiment I am actually moving this tube with respect to burner, it is the relative position that matters. Now the starting perturbation, so we saw that there are two kinds of instabilities, what we call linear instability and non-linear instability. So if you are in a classically stable configuration it will start off with any arbitrarily small disturbance, and the world is always having some arbitrarily small disturbance, any small disturbance it can take off. But if you are in a bistable region, that means either you can go to a limit cycle or you can come back to a fixed point, then you need an appropriate initial condition which you will have to give it with through some other means by using a loudspeaker or whatever. So in these pictures that I showed we are starting with we are looking at linearly unstable region, so it will start spontaneously out of any small disturbance. Any small disturbance, for example if you do experiment here you can hear the hum of those instruments behind or hum of the air conditioning and or somebody may move his hand or sneeze or something, anything will act. In when you are in a subcritical region it depends on what kind of initial condition and so on. So it depends on the type of the type of the signal, the type of the initial excitation. Some excitations are very good, even people, I mean it's like that, somebody tells you don't ignore, somebody else tells you you listen to it, so it's something like that. Okay, so I hope it's clear. So in these pictures we are starting from we are under linearly stable conditions, so any perturbation will suffice, and I didn't do anything here to start, I mean it just spontaneously came on. Any other questions? Okay, you can see this kind of thing in pretty much any experiment, like in the Ricci tube we saw very same kind of thing. Look at the thermoacoustic engine, you will see similar things, any combustion instability, these are, so there are some common underlying features, and of course in spite of the fact that the way the heat release rate respond will be different in different experiments. For example in the Ricci tube we saw that there it is the cylinder heat transfer, how it oscillates when the flow oscillates, but here that is not the case. Here it is the flame that is wrinkling. In the Ricci tube there was no wrinkling or anything, it is just the heat transfer in and out when you were blowing back and forth, whereas here it is there's wrinkles and you are having wrinkling. If you are looking at a diffusion flame, what would be oscillating the heat release rate? Now, suppose you have a diffusion flame, what would be oscillating? Let us say we do not oscillate the mass flow rate, so let us say we are choked the incoming flow. No, we are having, let us say, fixed fuel flow rate coming out for, yeah, velocity fluctuation, what does it do? Right. No, that is in premixed flame, diffusion flame.
It's going to change the diffusion length.
It is going to change the mixing.
Yeah.
So it is going to change the mixing field, so the way the fuel and air are distributed, so it is going to change the flame. So in each situation, in some other situations like what Mr. Kamble said, you have you have oscillations and your fuel flow rate can fluctuate or the air flow rate can fluctuate, your equivalence ratio can fluctuate because you have a delta P across an orifice, and as the delta P increases and decreases, because when pressure goes up the delta P comes down, when the pressure comes down delta P increases, so you are having a oscillating delta P on the injector, so you can have an oscillating flow rate. So in different combustors you have, or different geometries, different configurations, we have different mechanisms of the heat release fluctuating. So you have to study, so there is no general prescription as to how to calculate the heat release rate. For example, in one case you study a hot wire, flow over a hot wire, in another case you study wrinkling of a premixed flame, in another case we study how the mixing field changes in a diffusion flame, in another case we study how the injection is oscillating, as Ganesh pointed out. So in each situation there is a different mechanism as to how heat release fluctuate, but in spite of that there is some commonality as to how the oscillations are coming out, this linear stability, non-linear stability, bistable region, globally stable, globally unstable, those are all common themes in spite of the fact that these experiments have quite a bit of differences. Is that clear? It's a good point actually. Any other questions? Okay, so here the topic today is wrinkling of a anchored flame. Now you saw that these flames were anchored, that means they were fixed to the burner. These are burner stabilized flames. So the at the burner you have a local recirculation zone no matter how small it is, and then that will hold the radicals there and you can have the flame sit on that so that it does not blow off. But you can also have flames which are standing off, or you can because you may not have a flame right at the burner and it may just stand off and lifted, and then the heat transfer there, the dynamics of the heat transfer at the burner lip, that will control how much the flame is standing off and so on. So those are complicated, and my idea is to reduce everything to toys. So everything, once you have a formula for heat release or expression or a calculation procedure, computer program, anything for the heat release rate, then we can go back to our old procedure either in time domain or in harmonic domain, and then either calculate the stability in time domain with our numerical integration and linearized operator non-normality blah blah blah, or we can look at it in the harmonic domain and look at the eigenvalues, eigenvector, stability of the modes. So all those procedures will come in. So only thing that is needed is to get a way to calculate the fluctuating heat release, and that is the objective. Is that clear? So I have instead of studying calculating heat release rate in a flame, that is a very general objective. So I have brought down the objective to wrinkling of an anchored premixed flame. So I have simplified the problem quite a bit. So let us first take a look at the geometry of what we are studying. So this is the lab coordinate system, x and y, and let us say this is like a mean flame. So what is the concept of the mean flame, or let us say there are no fluctuations and we happen to have a steady flame. How does a steady flame exist for a premixed flame?
Premixed fuel air velocity.
Okay. What is a flame velocity or flame
The
speed?
velocity at which flame will propagate if the fuel air mixture were stationary.
Okay, so you have a fuel air mixture that is stationary, and if you light up the flame it will try to propagate. And how does it propagate? How does a premixed flame propagate? This is not a combustion class, but I think we have to deal with combustion. So how does the flame propagate?
There is a reaction zone
Reaction.
and a heated premixed zone,
Premixed.
then a reaction
Yeah.
zone, and as soon as reaction is over at every stage it will accelerate.
How does the how does the reactants know that we have to receive the flame? Flame is coming. How does it know?
Deflagellation or detonation?
Heat transfer and diffusion. I mean heat transfer due to conduction, and then the species transport due to diffusion. You have to have some kind of preheating so that the thing will catch fire, have the flame going, and we need radicals to get the reactions going. We need hot radicals, so that will also diffuse through the flame front. Heat will also diffuse through the flame front, and you go. And So it depends on the conductivity, diffusivity and the amount of heat released and so on and so forth, the flame speed. So in this is the crux of the matter is flame speed. So flame is trying to propagate, and the speed at which the flame front moves into a quiescent medium of reactants, that is called the flame speed. So that means we are talking about a moving flame front, but if you light up a Bunsen burner flame, you will see flame nice and standing like this. So as Vishnu says, the flame speed, which actually corresponds to the consumption, it corresponds to the consumption rate of the reactants. Okay, so you have flame speed which is being balanced by the velocity of the mixture, or in other words, you have a certain rate at which reactants are consumed, and as long as you supply as much as it is consumed, then you will have flame front standing. Okay, this is clear, and that is how we are getting it in a Bunsen burner or something like that. So we will call this angle theta. So this is our lab coordinates. We will also, for convenience, we will have another set of coordinates which is eta and psi, and let us say this is our flow velocity. Now we will have a, so this orange line is representative of the premixed flame, which is wrinkled. Okay, and this zeta equal to zeta of eta comma t. So this coordinate is eta, this is psi, and this is zeta, and the reason for trying to set up things in a flame fixed coordinate system is that again result will look simpler, although sometimes it may be advantageous to do in the laboratory coordinate itself, but for the time being we will do this way to keep things simple. So this is the geometry, and this angle theta is the angle the mean flame makes with respect to the laboratory coordinates. So in general I can say r equal to f of t, where r is the spatial coordinates of the flame. So I can actually say, you know, g of r comma t equal to r minus f of t, and I can say that, so if I define a function r minus f of t, where f of t is the location of the flame at any instant, with r, so this just means the location of the flame is changing in time. Okay, so if I define a function like this, and then it has to be 0 at the flame, so this g going to 0 is the flame, if it is not 0 it is on this side or that side of the flame, and we have to track the g equal to 0 surface. So that is the idea. Okay, I hope this is clear. You have r equal to f of t, so we can also write the same thing as r minus f of t is 0. So we call a function g of r comma t as r minus f of t. We know that at the flame r equal to f of t, that means at the flame r minus f of t is equal to 0, which means g is 0. So g is 0 corresponds to the flame, otherwise it is on this side or that side of the flame. So we track the g equal to 0 surface.
F of t, r is any arbitrary?
I mean not arbitrary, I mean flame location. I just gave r in general 3 dimensional, now I will write specifically for this. I mean you can write this for any complicated flame, now specifically for this I will write. So a point on the surface will move with a velocity given by, so let me write, so you have a gas velocity, and we also have SL, which is the flame speed. So let me write this, SL equal to, we are looking at laminar flame, and SL is the laminar flame speed. So if V is the velocity of the local fresh mixture, and SL is the flame speed. V is the and we need to know what is N. N is the local normal. So the unit vector N goes like del G over modulus of del G, which is the local normal to the flame front. So I hope so far is okay. Yeah.
Since there is fluctuations here,
yeah.
how can we be sure that we can use laminar flame speed?
Yeah, it's a very good question. Yes, when you are wrinkling, the curvature of the flame changes, so your local heat transfer and all that changes. So laminar speed is laminar flame speed is a function of many things, including the flame curvature, and so SL itself changes. So he has stumped me, but I am a theoretician at this moment, so I can put SL varying, and then I will get a more difficult problem. So I assume SL to be constant, and I will say that the wrinkling is small. So it is just an assumption that SL is constant. The equation is right, but SL may not be a constant. Okay. Yeah. Any other questions? So we are tracking the G equal to 0 surface. So dG over dt at the flame will also be 0, because we are looking at the sitting on the G equal to 0 surface. So this we can write as dou G by dou T plus partial derivative G with respect to partial T plus V flame dot del G. Okay, so it's straightforward. So now the question is how to write expression for G. So do you have to write a G field, solve for it, or is there some simpler way for simple problems where you can actually get the equation in a more straightforward way in terms of the flame coordinates, in terms of the flame shape, and then solve for the area fluctuation. So that is the objective here. So let me elaborate on this a little bit. So this equation can be rewritten as this, where we said that V flame is V minus SL times N, that is the imbalance between the velocity of the mixture velocity and the flame speed, and so that is what I put in here for V flame. So this we can expand as dou G by dou T plus V dot del G equal to SL, and we have this expression for N dot del G. So del G dot del G is this magnitude of del G squared, so this would be SL. So we can cancel this. So just to write it nicely, so this equation is referred to in combustion literature often as the G equation. So this is called. So now we have to see how we can simplify this for this kind of flame. like a cone flame or a tent flame or something. So here we have this as the flame departure of the flame from the mean position or something, or the local flame height. So the equation, so there we can say our G can be thought as see this is the coordinate psi, so we can say psi equal to theta of eta comma t. So we can say psi minus zeta of eta comma t equal to 0, and we can say this is G. Okay, is it clear? This is the flame height in this direction, so that is psi equal to zeta of eta comma t. So we just move this to this side and we call that as G. So now given G we have to get expression for del G, and then our problem is solved. So that is very peaceful. Del G equal to remember our coordinate system, so this is eta and this is psi plus dou G by dou eta into E eta. So dou G by dou psi would be, what is dou G by dou psi from this? 1, and what is dou G by dou what is it called, dou zeta, dou G by dou zeta, yeah. So this will be so this is the expression for del G. Is this okay? Straightforward. So given this, this will be square root of 1 plus so this is the expression for the magnitude of del G. So we need to evaluate this term V dot del G, that is the last thing left. So V dot del U psi E psi plus U eta E eta, taking a dot product with del G, which is so what is this? This is U psi minus U eta. So we substitute for V dot del G and SL times magnitude del G with V dot del G here, or the magnitude of del G here, and then we can get the final equation. So that would be, so remember that this was G, so dou G by dou T will be what? Yeah, exactly. Minus dou zeta by dou T, because psi itself then dou psi by dou T will not be there, you will have only this thing having a derivative, plus or we can rewrite this nicely as dou psi by dou t plus so our G equation has reduced to this simpler equation. We will try to write this in terms of, so at the moment it has both fluctuating and mean quantities together. We will write all the variables as a fluctuating plus a mean quantity and then subtract out the mean part and then we will look at the fluctuations and then maybe we will linearize it also, so that we will get some simple expressions which we can, if you have a linear differential equation, we can very likely solve it. So you would say u psi is u psi bar plus u psi prime and u eta equal to u eta bar plus u eta prime. So if you substitute this here, you will get dou psi by dou t plus u eta plus eta prime times dou psi by dou eta equal to u theta bar, sorry, u psi bar plus u psi prime minus SL into root of So the first thing that we do when you have mean and fluctuating is, if we can take a time average of this equation, we can separate out the mean terms. So if you time average these quantities, you will get u psi bar equal to SL. If you expand this, the binomial series, then you SL will come out here and this would be the mean equation. So this is what we started with, as at the beginning of the class I asked you how does the flame stay, and we said that the mixture velocity should balance the flame speed and then you can have a flame staying steady, and that is coming out of our analysis. So it is consistent so far. Now we have to wipe this out and we will subtract the mean and drop the nonlinear terms, and then you can get this is, of course I must emphasize, linear equation. So we have removed this mean terms and then we have linearized this term and we have this equation, and we have dropped this u eta prime dou zeta by dou eta prime, maybe that term is small because it is a product of two terms, and we are having assuming that your flame is displacing by small amount and you are also having a small amount of forcing, then we drop this term and then this is the way it is. So what is u psi prime? Yeah, what does this mean? It is the direction normal to the mean flame shape. So we are being forced by a velocity in a direction normal to mean flame shape, right? I mean, so if you have acoustic field, it has a certain velocity and pressure. The velocity has a component normal to the flame shape, and that is working as a forcing term. And what is the physical meaning of this equation? Yeah, so if you in steady state there is a, if there are no fluctuation, there is a balance between the mean flow speed or the reactant speed and the flame speed. Now if this is perturbed, then what happens, there will be a imbalance and the flame will either move in or move out depending on which way it is imbalanced. So that causes a wrinkle, and the wrinkles are actually propagating or being convected on this direction by this component of velocity in this direction. Okay, is that clear? So I think I will write this down, this interpretation. So for the steady flame there is a balance between so for the steady flame there is a balance between the flame front propagation velocity and the flow velocity perpendicular to the flame. So if this balance is perturbed, so that would mean u psi prime not equal to 0, okay, that is what is creating the imbalance, and then the position of the flame changes, the flame wrinkles. Because if the balance is changed, the flame will move that way or this way, that is what I mean by the flame wrinkles, and the wrinkles are convected along the flame front with the velocity eta bar. You can see from this equation, this is the convective term, this convex wrinkles so this is a simple equation, we can write a simple, integrate this in a straightforward way. Is this interpretation clear? I think once that is clear, everything else is clear. So if you define a characteristic speed as u eta bar, so let us rewrite this equation here. So let us say d eta by dt equal to u eta bar, then we can write this equation as d psi by dt plus, along this direction you can write by dt into, so this would mean that, sorry, so if you define a characteristic speed as d eta by dt equal to u eta bar, then you can rewrite this as d zeta by dt equal to u psi prime along this characteristic direction, okay, not in any other direction but along this direction. So along the direction you can integrate it because this is a full derivative. So integrate along the characteristics. So we will use primes as the dummy variables, dt prime. So we know that given this we can say T minus T prime equal to eta minus eta prime by u eta bar, okay, because this is a constant velocity here in this particular example. So this we can rewrite as 0 to eta this conversion. So this is the solution in terms of the characteristics. But more importantly, there is a underlying physical meaning to this. So the flame front, the position of the flame front is not determined by the present value of the perturbation velocity, but also by the earlier perturbation which happened upstream at the position eta minus eta prime, and which are now convected to the wave along the wavefront with a velocity with a convective velocity u eta bar. So so in this case the integral is not just a integral, but integral over the history of all perturbation, and which will introduce some kind of non-instantaneous or a time lag behavior, because you are having a wrinkle and the wrinkle was originated here, that then moved up here. So what is happening here not just depends on the velocity, local velocity there, but also the local wrinkle, which actually depends on whatever happened to this flame at some time t earlier. So you can clearly see this is bringing a time lag kind of time lag into the problem. So we already learned that time lags are very critical, and here there is a time lag coming because of this wrinkle which is propagating at u eta prime u eta bar, and this will play a key role in determining the phase, and this will and this time lag will be very important in determining whether the flame is driving or damping, okay, because of this.
Time lag will depend upon the flame shape, the angle between.
Right, so the flame angle determines what is the flame direction, what is the velocity along the flame, what is the velocity across the flame. So clearly time lag depends on this, and we will write, so we will do this in a harmonic domain, and there perhaps the interpretation of this may be simpler, and we look at what causes it, how we can make more sense of the time lag. But from this time domain solution it is very clear that you do not have just an instantaneous response, but there is a time lagged response, and also by looking at just this differential equation you see these rings are being convected. So when something is convecting, everything in the past will affect what is happening at this time. So stop here now.